Welcome everybody to the Good Data Podcast. We have another issues episode this week. Today we're starting our series on green data centers. I'm really excited about this. This is a topic that is near and dear to my heart. I have spent a lot of time optimizing data centers for energy efficiency, and I've seen a lot of boneheaded stuff as well as some incredibly brilliant engineering around data centers, and I can't wait to talk about it. Since this is the first of our series, we'll start with a bit of an overview and then dive right in with the first topic in the series, which is software. That's right, green software. I'm guessing that a lot of people haven't really thought about software as being a waste of energy, but have you ever accidentally copied a huge directory from one place to another, or maybe even lost it? That was wasted computation. It was a mistake, and maybe it took 5 minutes to finish copying. All of that was electricity that was wasted, and so were your nerves. And we'll take that feeling and multiply it by 10 because this is the sort of computation that happens every day across the world. And if we could stamp just a little bit of that out, we'd save billions of dollars, millions of kilowatts, and probably thousands of jobs. Let's go. The first thing I want to say is that there is no green data center.
There's no such thing as a green data center.
Right.
Though they are building some zero impact data centers in Europe, and primarily the Netherlands and Denmark and Sweden and whatnot, where they have a lot that decades now been focused on delivering renewable energy. But, here in the U.S., we have not had anywhere near as large of a focus and not provided the types of incentives that they have.
A data center is not a farm, but what we're talking about is minimizing the pollution and environmental impact while maximizing energy and water efficiency. There are a lot of choices out there for ways to make all this happen. We've seen pumped refrigerant, we've seen outside air, we've seen immersion cooling. If you notice, all of those are cooling related. It's because cooling is really the single biggest driver for data center efficiency from the standpoint of data center operators. But I want to take a step back for a moment. What is the most important piece of the stack for driving overall efficiency? Well, my interest in this got sparked around 2008 when I read a study by what was then Emerson Network Power, now Vertiv, called Energy Logic: Calculating and Prioritizing Your Data Center IT Efficiency Actions. Here's a quick excerpt.
While data center energy consumption justifiably gets attention in the industry, the gains in output and efficiency deserve a similar level of consideration. To put this in perspective, if the compute output in 2007 had stayed at the same level as 2002, data center energy consumption in 2007 would have been less than 1/8 of the 2002 level. This increase in compute output directly contributes to business and personal productivity and economic output, reduces travel and other non-value-added activities, enables real-time information for better decision-making, and supports the globalization of the economy.
Some of you have probably heard of this paper, but I think it's actually pretty obscure. But the base idea was that there's this cascade effect. So you run some computation that takes place on a slab of silicon, the processor, but the processor gets the power from its power supply. So if you have an inefficient power supply, you aren't getting the compute per watt that you want. But that power supply has to be backed up by a UPS, and now you're using both the baseline processor power and the extra power for the inefficient power supply, and then you have to cool off all that equipment. So there's this cascade of one inefficiency causing a much greater problem if you go all the way up the chain. Now, a lot of manufacturers realized this, and they moved to much more efficient power supplies and really started to do a good job at improving that efficiency. When the paper was originally written, it said that it was 2.8 watts to every watt of computation, but now I think that's improved a lot. Maybe it's closer to 2.3 or 2.2. And what hasn't necessarily kept pace is that I see a lot of legacy hardware out there. There are old computers chugging away, even though 20 of them could be replaced by a single virtual server or moved into the cloud or put into some other high-performance environment and use a 20th of the cost. Processors improve on their energy efficiency somewhere in the order of Moore's Law, or at least they used to, every 18 months or so. So if you get new chips, you'll get more computation out of them, although that seems to be decreasing every year. But let's take another step back. Let's say you've made all your hardware super efficient, your servers are completely up to date, your power supplies are rock solid. What about the software? Wasted computation like 20 times replicated backups or over-provisioned virtual servers or poorly coded workflows. These are things that literally burn through your energy bill and generate zero revenue. This comes down to management. It comes down to systems, oversight, responsibility, all the things that are hard to do. So how do you fix it? How do you incentivize your IT department not to back up the backups of your backups, not to leave a server running that has not performed a single function in 10 years, not to run a bubble sort when they could traverse a semantic tree, do it in 1/1,000,000th of the time? Okay, so the last example would probably never happen, but you understand that every improvement in software performance actually has this huge cascade effect, saving on processor cost, electrical distribution, cooling, everything. There are programmers out there doing yeoman's work finding the absolute fastest algorithms for a given purpose. These people are brilliant, but there's room for that type of performance alignment, not just at the high-performance computing world, but also in your regular old business, in your server closets, everywhere. So I want to go through the 5 main software issues that waste the most electricity. I've touched on some of them, but I want to get into a little bit more depth. First one is zombie servers. Second one is over-provisioned servers. Third one is unneeded server segmentation. The fourth one is shitty code. The fifth one is a misalignment of incentives that causes all this. Okay, so zombie servers. Let's dive into the monster on the docket. Here's a quote from a May 12th article in Computer World titled, "A third of virtual servers are zombies," and it had the subtitle, "Idle virtual servers may be more costly than similarly idle physical servers."
New research finds that 25% of all physical servers and 30% of all virtual servers are comatose. These are systems that have no activity in the last 6 months. The problem with comatose, or zombie, physical servers is well known. Past studies have routinely put the number of undead enterprise physical servers in the 20% to 30% range. But this latest research looked at virtual servers as well, and they may represent a significant cost to IT departments. That's because users may be paying licensing fees on their virtual servers, as well as on the software they support, said the researchers. Comatose servers, both virtual and physical, may also represent an unappreciated security risk because they aren't patched and maintained, according to the research paper by Jonathan Coomey, a research fellow at Stanford University, and John Taylor, a partner at the Anthesis Group, a consulting firm.
So I found that really interesting. The idea that virtual servers and physical servers are both causing this over allocation of compute resources. And if you think about it in a virtual setting, that's an easy enough thing to notice. You have dashboards and things that actually show how much a given virtual server has used. Hopefully you have a high quality hypervisor, you probably, whatever it is, Hyper-V. Then you should know that you have these servers, but a lot of people don't do anything about it. A lot of companies don't really pay attention to that. They've spun up a development server, or they've spun up a server that they thought would do more work and it isn't, and they never spin them down. And I hadn't thought about the idea that that's a security risk too, that it's a possible threat vector, that if somebody just spun up a server randomly and didn't really care about it, then they're not going to take ownership of it, and it is likely to allow some kind of malicious software in. So zombie servers are things that I've seen in data centers, especially legacy data centers, where there have been a lot of hardware changes over time, and there's been a lot of staff changes over time. So the sysadmins who were working on a given server have since gone elsewhere and left behind a server that nobody has really looked at. And I said this advice already on the podcast, but I'll say it again. It's worth looking into Active Directory and trying to find the system admins for a lot of these servers. They should all be covered in Active Directory if you have a unified login for everything. You can go in there, or whatever other unified login service you're using. You can go in and find the sysadmins, email them, and say, hey, are you actually using this server? And what I've seen is that if they don't respond in X number of months, you literally unplug their network port for a little while and see if they say anything. And if they don't say anything after a month, then that server's gone. And the great thing about that is it is literally wasting you money. It's wasting you warranties, licenses. It's wasting you energy. It's not just a green issue. It's definitely a money issue. Now, most of these are really, anything that we're talking about is a money issue too. Now, the one caveat to this is that, of course, you still need to have servers that are ready to go for elasticity and overflow, and there's definitely a reason to have excess capacity. That makes sense. There's nothing wrong with that. But we're talking about above and beyond that. We're talking about services and servers that actually are not being used, that will not be used. That's what a zombie server is. It's not over provisioning. That's our next topic. So let's go to that. Okay, so it's also a huge problem. Let's say, just for fun, that someone set up a server for the simple task of like sending out a single informational email like once every second forever. That server has to keep running. It's doing important work, but the workload itself is minuscule. You could run an app on a Raspberry Pi, like the size of a stick of chewing gum, that would do that. So here's an excerpt from an article by Nick Martin over at TechTarget called Over-Provisioning VMs May Be Safe, but It Isn't Sound.
Appropriately sizing virtual machines can be a difficult process with many unknowns. Allocating too few resources can starve a VM and lead to poor performance. Administrators wary of this potential problem may take the safer approach and allocate more resources than a VM needs. However, this over-provisioning wastes resources that other VMs could use. According to Andrew Hillier, the CTO and co-founder of SRBA,
we like to use an analogy to a game of Tetris. Workloads come in different shapes and sizes, and when you add them together, it starts to jumble up to the point where servers look like they're full. But, when you play Tetris more cleverly and move those blocks around, you can defrag capacity and get a lot more out of it. Sometimes people are doing all the right things with the tools they have at their disposal, but they can't fight this because they don't have anything that can help them play Tetris better.
So, one way to think about this is that over-provisioning can happen in physical servers too. You could buy the latest 12-core Xeon processor that would just send out one email every minute. It's definitely something that happens and has happened and will happen because people want to cover their ass. And that really is a problem. It's a misalignment. It's a waste. It's a huge waste in certain circumstances. And some new technologies can actually kind of exacerbate these issues, like containers, for instance. Because they can spin up and spin down so quickly, they can suddenly create this huge amount of compute out of nowhere, where the bottleneck would actually happen slower if it was a normal virtualized server spinning up. So suddenly you've got these containers pop that happen very quickly, and so you have to scale to that high level. So it's great for performance. It's wonderful. Containers are wonderful for being able to get that elasticity, but that means that you have to have so much additional compute for that kind of stuff. So you are almost stuck with over-provisioning. There are ways to handle that, and it's almost like an opposite problem. Like cloud, for instance, you don't want to allow too much compute to be allocated because then you're paying out the nose. So there's some sort of fine line between performance and reliability and not over provisioning and wasting money and electricity. And I do like to think about this in green terms. Every extra compute cycle, every second, every minute is taking up not only that compute energy, but also the cooling energy and the UPS energy. And when there's a outage, it's taking up the diesel fuel for the generators. There are 100 different ways in which reducing software complexity, making software better, is actually reducing the total energy footprint of your entire data center. It's really something to think about in those terms. That software isn't benign. It is the engine of all this. And not only should software be secure and stable and efficient, but it should be green too. So the next one I've called unneeded server segmentation, but I need to drill down on that a little bit more, because what I mean by that is that not everything has to have its own server. Not everything has to have its own virtual server. That's a normal thing. If there's an application, it's often relegated to its own server with its own services and so much behind it. But the problem with that is that, like I was saying before, there's so much overhead to having a server, that a server has to have an operating system. It has to have a database behind it. So it might have object storage, block storage. It might have all these pieces that make it up. So there are ways around this, but some of those create stability problems. You often don't want to have multiple applications on the same server because they could crash the server. It makes sense. I totally get that. That's why we have virtual servers, and that's why we sometimes really under-provision those virtual servers. But you could provision a server that actually just had a lightweight operating system on it. You don't have to provision a Windows server every time. It can actually really save a lot of extra compute if the server itself is incredibly low. I mean, maybe it's one core on the virtual server. Maybe you can make do with a lot less with a lighter weight framework. Now, another thing that I want to introduce here is the idea of serverless compute, which is a frustrating term, but I really like the idea because it incentivizes what we're talking about. It incentivizes well-written code that will run only when it needs to be run in an environment where compute resources are shared and allocation is based on a need that is managed by the cloud provider. There are a number of different serverless architectures. I'm going to talk about Lambda for a second, which is the AWS product. The crazy thing about Lambda is that you can just take some code, let's say some Python code, and put it into the Lambda framework, and then you'll just have a call that says, all right, run that code. And without having to deal with server maintenance, Amazon server somewhere out there, make that code run. It'll interface with your S3. It'll interface with all your other Amazon cloud pieces or other storage pieces, and be able to complete whatever task it's given without you having to worry about anything on the back end. And it's a growing piece of the industry. This is definitely more of a software thing. It's not really, it's a cloud architecture thing, and it's mostly for actual software designers, but it is definitely something to think about, even in enterprise, similarly to what I was just saying, where there's a server somewhere that sends out an email, X number of emails. Sometimes when those things happen, people have just a server spinning someplace when it has to happen. That has to happen once a month or something. So that, that server that has to do that once a month for an hour is sitting there for the entire rest of the time running, even if it's somewhat idle. So figuring out ways to reduce that is incredibly helpful. Now I'm going to go do an excerpt from the Amazon website that explains what Lambda is and what is serverless architecture. It's called Building Applications with Serverless Architectures. And it's on Amazon.com.
What is a serverless architecture?
A serverless architecture is a way to build and run applications and services without having to manage infrastructure. Your application still runs on servers, but all the server management is done by AWS. You no longer have to provision, scale, and maintain servers to run your applications, databases, and storage systems.
Why use serverless architectures?
By using a serverless architecture, your developers can focus on their core product instead of worrying about managing and operating servers or runtimes, either in the cloud or on-premises. This reduced overhead lets developers reclaim time and energy that can be spent on developing great products which scale and that are reliable.
What is the use cases of serverless architectures?
Coders can build web applications and mobile backends in a faster, more agile way. They can serverless architectural patterns that reduce the operational complexity of running and managing applications.
Okay, so I've talked about it for a while, but I'm going to take another quote from Hacker Noon. There's an article by Faizan Bashir that asks the question, what is serverless architecture? What are the pros and cons?
The cost model of serverless is execution-based. You're charged for the number of executions. You're allotted a certain number of seconds of use that varies with the amount of memory you require. Likewise, the price per millisecond varies with the amount of memory you require. Obviously, shorter running functions are more adaptable to this model with a peak execution time of 300 seconds for most cloud vendors.
So I've been thinking about Lambda a lot, in terms of a green technology. I don't know how much compute architecture is back there spinning disks that are actually not operating and how much that's just throwing energy up into the clouds, even more than it would be on your own data center. So I don't know if there's a green technology. It actually would take a huge, huge amount of investigation that probably Amazon wouldn't want to provide in order to figure that out. But the nice idea of it, that you're using shared resources that, limit the idle because you're not doing anything that's idle. Other people can use the resources while you are idle. And you're maximizing your available resources. So if you need to run something, you'll just spin up you'll spin up instantly. You don't have to really do anything. There are a lot of limits to it though. Serverless is very complicated to implement. There's security issues, there are safety issues, there is stability issues. You're only allowed to have so many instances running at the same time. You're only allowed to run a single instance for a such and such time. So there are possibilities that basically if you screw up your code execution, you're going to do a denial of service on yourself. You're going to use up all the compute resources that you have so that your program will just crap out because it didn't have enough compute resources available. So a lot of issues, but I'm very excited about it because the thing that it does really well is that it incentivizes right-sized code. Instead of incentivizing, huge operating systems in the background, it incentivizes the idea that you are charged for compute millisecond. So it incentivizes you to use as few milliseconds as possible, and time and computation pretty much equals energy. So by reducing those milliseconds, you're reducing your energy. We have to take a break. We'll be back in just a second. Today's episode is brought to you by Greenlane Design. Greenlane is a full-stack design, build company focusing on data centers. They've developed projects from BOD to finished turnkey build for many different types of companies, including colocation, high density, and enterprise. If you would like to get a free assessment, go to greenlanedesign.com, click on contact, and mention the podcast. And we're back. Okay, let's move on to shitty code. And I hate to call code shitty because it's really hard to be a programmer. I did it for a while. It's hard. And as much as I learned, I also screwed up so much, and I wrote my fair share of shitty code. But the point is that not all code is equal. So For anyone who knows what a bubble sort is, you know that different algorithms operate at different speeds. And like I was just saying, different speeds create different power draws. And in computer science, we use this thing called big O notation, which is just this way of saying, how long is this going to take if we do it 10 million times, 20 million times? If we just keep doing this over and over again, certain things, if you do it once, it'll happen quickly. But if you do it 10 million times, it'll take forever. And certain things, you do it once, it'll happen quickly. And if you do it 10 million times, it'll also happen quickly. So the analogy I like to use of this is with a deck of cards. Let's say you're trying to find the ace of spades. So if you're trying to find the ace of spades in a shuffled deck, you basically have to go through all the cards in the shuffled deck to find that ace of spades. But let's say somebody has a non-shuffled deck. Well, then you find the ace of spades in an instant. So even if it was the 10, you could flip to where the 10 should be in a non-shuffled deck, and you'll find the card very quickly. So that is an algorithm. That's a way of thinking about efficient code and quickly producing algorithms that actually make a real difference. Instead of having to, every time you're finding the card, sift through the entire deck, you can go right to it. So that's at the heart of computer science, is this idea of efficient code, big O notation, writing quick code, optimization. But it's not really talked about to server admins too much. But the fact is that it really should go all the way up and down the IT stack. That sometimes newer code is the most optimized code. The program has been improved, made quicker, faster, but a lot of times there's a lot of bloat that's added to computers too, and software. And you think of, I hate to use this example because I have no problem with Apple, but iTunes. iTunes, when it first came out, was lightning fast because there was nothing to it. There was no extra stuff. It just worked because all it did was play music. But now there's like 30 different pieces to iTunes, and it takes a long time, much longer to load. And really all it's still doing is playing music and files. It's not too much different, but now there's all this bloat to it. And so I want to say that new software is optimized, but that's not really the case. It should be. Software developers should be incentivized to make optimized software, but they're not. The one group I think that is doing a fantastic job at optimizing software in this way is mobile. So mobile developers really are good at looking at how much power it's drawing so that they don't drain your batteries, because people actually complain about that. So they have this incentive to make sure that their code is running optimally. And data centers do not ever look at that. Almost no enterprise architectures, almost no hyperscale architectures really seem to care about the amount of energy used. The speed they certainly care about, but sometimes speed can actually increase the amount of energy used. Let's take parallel computing, for instance. Let's say, so certain computation can happen on just one processor, or it can be spread out across 1,000 processors. And it'll happen a lot faster if it's spread out over 1,000 processors. But the problem with that is that each of those 1,000 processors has its own overhead. So sometimes, not always, parallel computation actually is more energy intensive than non-parallel. One caveat to that is GPUs. If there's a custom built solution like a GPU that is running parallel computation, then that computation can happen that much faster. So let's move on to what drives all this, which to me is the misalignment, or at least misalignment from a green perspective, of incentives that software designers and sysadmins and most of the people who actually work in the data center environment do not have an incentive to do anything green. Sometimes the facility operators do, but really it's the developers that would never even think about that sort of thing. And most of what gets incentivized is uptime and performance, which, in a web architecture, that might just be engagement, that the KPI for all of this is engagement, which then means that they don't care at all about this green perspective that we're talking about, that it doesn't enter into it. That's why we're having this exponential growth of data centers. That's why we're having so much power being eaten up by these systems. It's that to get the millisecond performance to everyone's computer so that they'll buy Amazon a little bit quicker, they have to put thousands of servers out there that are getting to your search so quickly that you don't even see it. It's an amazing architecture. It's amazing that websites are served that way, that Amazon is able to get you exactly the toy that you want, or that Google serves up the search as quickly as it does. But by only incentivizing those things, uptime and performance, you're not really optimizing for cost in some ways, but also energy. So I think there needs to be a check and balance, because at this point we really are increasing the amount of power that we're using for compute, especially in data centers, really faster than is feasible. If we were to keep growing at the same rate in terms of energy use, we're at 5% now. We could be at 10% of global energy use in data centers in 10 years, and then 20% in 20 years. It's growing at an exponential rate, and that can't continue. And, there's a couple things that I think help with this. One is that software should be updated as often as possible, that it's worthwhile to use like non-bloated, lightweight code, and also OSs. You could use Tiny Core Linux versus Windows. You can make sure that, all of your OSs are still supported. Make sure that there's no malware running on your systems. That is a huge, huge waste of compute resources, not to mention all the other horrible things about it. And also think about when giving incentives, especially green incentives for enterprise IT staff, that you incentivize the total energy reduction, not just the PUE reduction, because PUE, as I was saying earlier, that reduces that overhead number, it reduces the cooling, but it doesn't reduce the actual usage by the compute. It's almost like compute is sacred in the data center world, and I don't think it should be. And, always keep in mind, of course, that there needs to be overhead, there needs to be extra servers running for uptime and scalability and DR, and there's no way around that. But you can put some of that elasticity in a public cloud if possible, or a private cloud, or some shared compute or warm compute that can spin up or have a time to spin up. That, not everything has to be ready at a moment's notice in every corporation or enterprise environment. I know a website has to be ready to go at a moment's notice. We're not talking to you right now. We're talking to enterprise. I think even internet-facing companies, internet-facing software, I think overdoes it a lot of the time. There are other ways to be able to get elastic compute than over-provisioning servers and bloating software. And all this comes down to business intelligence and management and cost comparison software and dashboards and things that actually get, well, I'm not a huge fan of dashboards, but things that actually get to the heart of what compute is actually being used, what can be measured. It's very possible to see the ages of equipment, see the cost of warranties, see the cost of licenses, look at the ages of the software, see if there's zombie servers that are not running. This is all stuff that can be done if IT put more of an emphasis on it. But it's a difficult thing, and it's not generally what is done right now in a lot of companies. It's getting better, and I just want to see it done more. So, just realize that I just wanted to bend your thinking on this. I have never heard an application engineer talk about green code personally. I've read articles on it, but, it just doesn't seem to be in the zeitgeist. So, keeping track of hardware age, cloud provisioning, software optimization, they can save money and they can improve resilience, and you can do it. Well, that's our show. I'd like to thank Green Lane Design for sponsoring this episode. Please go to their website, ask for an evaluation, and mention the podcast. Also, please make sure that you follow us on Twitter. Our Twitter handle is data_good. You can find me on LinkedIn. Just search for my name. And we'll talk to you next time on the podcast.